Hello, my name is Gabriel Cosio. I am currently a PhD student in nanoscience at the Center for Research and Higher Education of Ensenada, and at the Center for Nanoscience and Nanotechnology, and this is my master's thesis work, which explores the potential of zinc germanate for lithium-ion storage. As we know, energy storage is essential for both everyday life and industry to ensure energy is available when needed. However, commercial lithium-ion batteries face capacity limitations due to the use of graphite in their cells. Consequently, there is a need to design and develop new materials to replace graphite. With this goal in mind, we propose the use of zinc germanate-based anodes. The zinc germanate nanoparticles were synthesized using the Pechini method, a polymeric precursor technique. In this process, the precursors, germanium oxide and zinc nitrate, were dissociated in a 70% nitric acid solution. Subsequently, tartaric acid was added as a chelating agent, and the mixture was stirred for 24 hours. After this period, the solvents were evaporated to obtain a zero-gal, which was then calcined at 1300 degrees Celsius to yield a white powder. The powder was characterized using scanning electron microscopy, X-ray diffraction, UV vis spectroscopy, and Raman spectroscopy. The results confirmed the hexagonal phase of the material, its chemical composition, and a band gap of 4.49 electron volts. Once the desired material was confirmed, it was utilized as the active material in electrodes for coin-type cells. The initial results from cyclic voltammetry revealed intense current peaks during the first cycle, attributed to the formation of the solid electrolyte interface and initial reactions. Following this cycle, we were able to identify alloying and conversion reactions for each observed peak. Additionally, studying voltammetry at various scan rates allows us to calculate the capacitive contributions of the electrode. These contributions arise because the nanostructured material has a large surface area, facilitating ion interactions with the surface. An increase in capacitive contribution with higher scan rates was observed, as higher speeds provide less time for ions to insert into the structure and react. A galvanostatic cycling process was conducted. The first figure illustrates the charge and discharge profiles at different cycles and a current density of 200 mA per gram, showing capacities of 410, 378, and 450 mA per gram for the first, 100th, and 200th cycles, respectively. The image on the right displays the electrode performance over 200 cycles, showing a trend of increased capacity beyond 80 cycles, with an efficiency of 99.9%. This image also shows capacity measured at various C rates. Furthermore, electrochemical impedance spectroscopy was performed, revealing three distinct regions in the impedance spectra that correspond to different resistances within the cell. The first region represents the electrolyte resistance, followed by the charge transfer resistance, indicated by the observed semicircle, and lastly, the straight line representing ion diffusion within the structure. A subtle increase of 30% in charge transfer resistance was noted between the fresh electrode, prior to ion insertion, and the charged electrode with ions inserted, attributed to an increase in electrode volume caused by ion insertion. In addition to the experimental work, a computational simulation study was conducted using density functional theory (DFT) calculations. The first image illustrates the minimum energy diffusion pathway for the first lithium-ion Li. It shows a minimal energy barrier of 1.42 electron volts along the 111th direction, where a tunnel in the structure allows the ion to be surrounded by oxygen atoms, facilitating easy diffusion without altering the structure. After identifying the pathway and minimum energy positions, lithium ions were inserted into the material. For this material, it was calculated that up to 14 ions can be stored per molecular unit, providing a theoretical capacity of 1,400 mA per gram. The formation energies and volumetric expansion for each inserted ion were calculated, demonstrating thermodynamic stability during lithium insertion with a maximum volumetric expansion of 175%. The open circuit voltage was also calculated, showing a profile similar to the charge and discharge curves, confirming the theoretical capacity of 1,400 mA per gram. The final image depicts the structural changes observed in the primitive cell of the material upon ion insertion, including a complete loss of symmetry and the apparent breaking of germanium oxide and zinc oxide bonds. To validate these findings, first principles molecular dynamics simulations were performed to obtain the radial distribution functions. These functions indicate the probability of finding an atom relative to another as a function of radius, effectively representing the bond distances between different compounds. The results show the expected compounds along with their respective functions. During the lithiation process, secondary phases form, and we anticipate the breaking of primary bonds. The following image displays the radial distribution functions with 6 ions inserted into the structure. A decrease in the intensity of peaks associated with germanium oxide and zinc oxide is observed, along with the emergence of bands attributed to lithium oxide, lithium zinc, and lithium germanium compounds. The final graph illustrates the complete disappearance of peaks related to germanium oxygen and zinc oxygen bonds, demonstrating the complete rupture of these bonds, with lithium oxygen, lithium zinc, and lithium germanium bonds prevailing. In conclusion, it can be confirmed that zinc germanate nanoparticles synthesized via the Pechini method can be effectively used as active material in lithium-ion batteries, facilitating diffusion and reversible conversion and alloying reactions. Additionally, theoretical calculations showed low ion diffusion energies and a volumetric expansion of 175%, which is moderate compared to the volumetric expansion of germanium oxide, and revealed potential secondary phases in the electrode. Thank you all for the attention.